The reason many energy efficiency and green building programs have adopted ASHRAE Standard 62 is to address occupant health concerns related to air quality. In the last lesson, I quoted the stated purpose of ASHRAE Standard 62.2 2013. This standard defines the role of and minimum requirements for mechanical and natural ventilation systems and the building envelope intended to provide acceptable indoor air quality in low-rise residential buildings. That's an interesting phrase in there. Acceptable indoor air quality. What does that mean? Well, the standard defines it for us. It says acceptable indoor air quality is air toward which a substantial majority of occupants express no dissatisfaction with respect to odor and sensory irritation, and in which there are not likely to be contaminants at concentrations that are known to pose a health risk. That seems fair enough. But what causes dissatisfaction or irritation, and what are the contaminants that are known to cause a health risk? Indoor air is generally less healthy and more objectionable to the occupants than outdoor air. That's because we add contaminants to it. We add moisture by cooking, bathing, and cleaning, and maybe from roof leaks and groundwater, and we even exhale and perspire moisture into the air. We add household chemicals from cleaning, hobbies, and even off-gassing from furniture. We add dust and other particles like pet dander, and sometimes we add tobacco smoke or combustion byproducts from poorly vented or unvented appliances or from candles burning in the house. These are the things that cause dissatisfaction, irritation, and health risks. So how do we keep the level of these contaminants low enough that they're not objectionable or unhealthy? Basically, it comes down to some simple concepts. First, we try to minimize the amount of them that get into the air in the first place. We call that source control. Then, if they do get into the air, we remove some of that air from the house and replace it with fresh outdoor air. We call that ventilation. And finally, we can attempt to remove particulate from the air. We call that air purification or filtration. ASHRAE 62.2 doesn't discuss source control very much. You can find that information in other places. It does discuss air filtration, and I'll review that in one of the lessons. But the primary focus of the standard is on ventilation. Most of the text covers ventilation rates, devices, and methods. When houses were built a century or more ago, the quality of the air depended on natural air leakage. Houses weren't sealed very tightly, and leakage carried stale, contaminated air out and fresh air in. But as time has progressed, we've built houses tighter for improved comfort and energy efficiency, and we've begun to add fans to provide additional air exchange. We can divide these fans into two categories. Spot ventilation, which is called local exhaust in the standard, means exhaust fans that are located at the largest sources of contamination. This is usually bathrooms and kitchens. These fans run intermittently, only when the contaminants are being generated, and this is very common in houses today. Mechanical ventilation, which is called whole building ventilation in the standard, is less common. It means fans that run continuously, usually at a low flow rate, to provide air exchange for the entire house. Each of these types of ventilation has advantages and disadvantages. Natural leakage is always present, and it doesn't require any occupant action to make it occur, but it varies with weather conditions, so there are times of the year when it provides little air exchange. The occupants have no ability to control the rate or timing to suit their needs, and they can't control where the air comes from. It might be coming up through a damp crawl space. Local exhaust does very well at targeting big sources of contaminants, but it only runs when the occupants turn it on. If they don't use it regularly, it's not very effective. Mechanical whole building ventilation provides constant year-round exchange, and it gives the occupant some control over the flow rate. But that's only if the occupants understand and use the system properly. In addition, mechanical devices are prone to failure and don't always get repaired promptly or correctly. To appreciate why mechanical ventilation is important, it's helpful to understand the different forces that push and pull air through houses. An obvious one is wind. Wind is moving air, so of course it will find its way in through leaks. Another is the buoyancy of warm air. Warm air is light, so it rises. When it's warm inside and cold outside, the house acts like a big chimney, with the warm air rising out of holes at the top. and another is mechanical fans, which can push air out or pull it into a house. Mechanical fans are the most controllable of the three, and we can use them to ensure adequate airflow. Let's take a closer look at the other two to understand why they aren't as reliable. When it's windy outside, that wind creates pressures around the house. It's fairly obvious that on the side the wind is coming from, the pressure pushes air into the house. But on the other side, where the wind wraps around, it creates suction that pulls air out. Somewhere in the middle of the house is a vertical neutral pressure plane that divides the intake and outlet sides. The two forces work together to accelerate air leakage. But this doesn't happen all the time. It only happens when there's a significant wind outside. The buoyancy of warm air is a more significant factor, especially in cold climates. The warm air rises and creates a positive pressure at the top and pushes out of any openings. This creates a suction at the bottom of the house that draws cooler air in through openings down low. Again, there's a neutral pressure plane that divides the two, but this time it's horizontal. This stack effect also doesn't happen all the time. It's highest in the winter, when it results in the biggest energy penalty, but it doesn't happen much at all in the warmer months. So there are significant periods through the year when these natural leakage forces don't do much to ventilate the house. This graph, adapted from a 2011 presentation by Paul Francisco, shows how natural air leakage varies with outdoor temperature. It shows a house with a desired ventilation rate of 50 CFM and a blower door reading of 2000 CFM at 50 pascals. When it's really cold outside, there's a lot of stack effect, and the house is overventilated. As the temperature outdoors goes up and approaches the indoor air temperature, the stack effect goes down and the air exchange rate drops. Of course, this is on average. There may be some windy days where it goes up. Once the outdoor temperature is warm enough, occupants start opening windows, so there's a bit more air exchange, but it's still not enough to reach the desired rate. And when it gets really hot outside, there can be a reversal of the stack effect if the house is air conditioned, with cold air pushing out at the bottom. From this chart, you can see that the house rarely gets the right amount of ventilation. It's usually either too much or it's too little. That's why we try to seal it tight and ventilate it right using mechanical fans. And keep in mind that intermittent local exhaust also contributes to whole building ventilation. When these fans run, they increase the air exchange. So if they don't exist or they have low flow rates, the overall building ventilation suffers. Now you understand the basic concepts. In the next two lessons, you'll learn how to calculate target whole building ventilation rates using ASHRAE Standard 62.